Hello everyone, and welcome to this video on force, distance, and work. So in this video, we're going to be taking a look at the equation work equals force times distance. So the first thing I want to do is address this parallel symbol. This is the two parallel lines next to the force in the subscript. So work is equal to force parallel times distance. What this means is that only the parallel component of the force, or the force component that's parallel to the distance that it's traveling, is going to do work on the object. So if we see here that we have some force at an angle indicated by the blue vector, and then a distance or displacement vector pointing to the right, so just a block sliding to the right. The force vector breaks down into two components, the horizontal component, which is F cosine theta, and the vertical component, which is F sine theta. Notice that F cosine theta is parallel to the distance it's moving. It is in the right direction. And F sine is perpendicular to the distance it's moving. So when we use force parallel distance, what we're effectively doing is we're pulling out F cosine theta from the force term if it's at an angle, and we're multiplying that term times the distance that it travels. And that's going to be the work done on the system. So remember that work can be positive, negative, or zero. Positive work is when a force transfers energy into the system. This would be when a force, or a component of a force, is applied in the same direction as the motion. So if you have a cart moving to the right, then if the force is applied also to the right on that cart, it's going to cause the cart to speed up, therefore adding energy to the system and doing positive work. So negative work then would be a force transferring energy out of the system. So if we take that same cart moving to the right, and then we apply a force to the left, say someone trying to slow it down or applying the brakes, that's going to reduce the kinetic energy or take energy out of the system. Therefore, it will do negative work. So a force does zero work when the force is applied perpendicular to the direction of motion. So thinking about that cart one more time, if the cart is traveling to the right, there are two vertical forces on that cart, one being gravity pulling down and the other being normal force from the surface pushing up. Both of these forces are perpendicular to the velocity, therefore they do not add nor do they subtract any energy from the system. So we'll take a look at a previously done problem where we had a textbook that was pushed and then it slides to rest. So we already drew the positive work from the hand and the negative work from friction, but just to illustrate this a little bit more, we can draw a diagram of the textbook and show that as it's being pushed forward, the force is in the same direction as the displacement, therefore it's positive work. As the friction force is slowing it down, the force is in the opposite direction of the velocity, and therefore that is doing negative work. So once again showing that this model, or this equation for work, should match up with our change in energy model that we've used before. Now that we have this new equation for work is equal to force distance cosine theta, we can pair that up with our previously used equation of work is equal to change in energy, and using these two equations in conjunction along with equations like kinetic energy or potential, we can solve for new and interesting things about problems. So this problem is now asking us to figure out how far does the book slide after leaving the student's hand. So we want to derive an equation for the distance that the book slides, and our answer can be in terms of the mass of the book, the coefficient of friction that the problem just gave us, and the velocity of the book, or the initial velocity of the book. So the problem that we're analyzing here is going to be from the moment the book leaves the student's hand to the moment that the book comes to rest. So we're going to block that off, and that's what we're going to be focusing on for this problem. So without plugging in numbers, we're going to revisit that equation that we set up from our previous video when we did this problem. And we know here that the kinetic energy that we start with in the second stage of motion when it leaves the hand, minus the work done by friction, should equal zero. So drawing a quick free body diagram for the book as it slides across the surface, we see that we just have mg down, Fn up, and those are the only verticals, so the magnitude of the normal force is equal to mg. And the only force pushing horizontally is the friction force pushing to the left. The student is not pushing it anymore because it's already left their hand. And the friction force has its own equation where the friction force is equal to the coefficient times the normal force. We can then rearrange this equation that we started with and say that the kinetic energy that the block has at the beginning is equal to the magnitude of the work done to take that kinetic energy away. So 1/2 mv squared will equal the force times the distance times the cosine of the angle between those two vectors. So we're going to take a look at the cosine term really quick. We have a rightward displacement vector and a leftward force vector. These vectors are parallel to each other, so the cosine term is going to equal 1. Technically, it should equal -1 since the angle between the vectors is 180 degrees, but we already took care of that negative sign when we recognized that the work is going to be negative because that force is taking energy away from the system. Now, starting from this equation, 1/2 mv squared equals force times distance. All we need to do is rearrange this equation for the distance that the object moves. So we're going to get distance is going to equal mv squared over 2 times the force, but we're not allowed to have force in our final equation. We can have m, we can have v naught, but the variable f is not allowed here. So we need to use the friction force equation to make a substitution in order to get rid of this variable f subscript f. So we're just going to use the friction force identity, which is friction is equal to mu times the normal force. But once again, we see here that the normal force is not allowed in there either. So we're going to make one more substitution, and we're going to say the normal force is equal to the weight force, mg. So our equation then becomes the distance is equal to mv squared divided by 2 times mu times m times g. But we see there's an m in the numerator and the denominator, so we can simplify. And our final equation becomes the distance is v squared over 2 times mu times g. And that's the full derivation for how far this textbook will slide based on this starting velocity. So take a look at one more example problem where we're throwing a baseball vertically upwards with some initial speed. So we're going to draw free body diagrams and energy bar charts for the baseball's energy at the following times. So the moment it leaves the thrower's hand, the moment it reaches its peak height, and the moment it reaches the thrower's glove when it comes back down. And we're going to assume that this is the same height. So quickly doing a sketch here, we should see that the ball goes up, it momentarily stops at the peak, and then it comes back down and reaches the thrower's hand. As far as the energy bar charts are concerned, the first stage, when the ball leaves the thrower's hand, it has some initial kinetic energy, so we're going to give it 3 bars of kinetic energy and label this K1. At the peak, the ball has stopped, therefore it has 0 kinetic energy, and we'll label this K2. And once the ball reaches the glove, it's picked up all of that 3 bars of kinetic energy again, so we're going to label this K3. And so looking at the work that happens here, we see that 3 bars of energy was lost or was taken out of the system between the moment it leaves the student's hand to the moment that it reaches the peak height. So this is going to be negative work done by the force of gravity. Gravity slows the ball down and takes energy away from the system, leaving it with 0 at the peak. But on the way back down, gravity is going to be doing positive work on the system because it is accelerating the ball back towards the ground. So we have another positive 3 bars of energy being added back to the ball system. So the free body diagrams should look the same every single time because the only force acting on this ball from the moment it leaves the student's hand to the moment just before the student catches it is going to be the force of gravity, or mg down. So all 3 of our free body diagrams are the same force vector, mg, pointing downwards. And so now we're going to look at an interesting question, which is, does gravity, the force of gravity, do positive or negative or 0 work on the way up and back down? So analyzing this, we know on the way up the displacement vector is upwards, but gravity is pointing down. So the work done by gravity is going to be negative here. But then on the way back down, the force of gravity has not changed direction, but the ball is moving downwards. So the force of gravity and the displacement vector are in the same direction. Therefore, on the way down, the force of gravity does positive work. So we get something kind of interesting here, where the force of gravity can do negative work and take the energy away from an object, and then it can do positive work and return that energy back to the object. So it's almost like the force of gravity is conserving the amount of energy or the amount of work that it does on an object. So this is a pretty powerful concept that's going to lead to the concept of potential energy as well as conservation of energy, which we'll get to in future videos. But that's going to be it on this video for force, distance, and work. Thanks for tuning in, and I'll see you next time.